We're about to debrief exercise 14 in Module 8. It's entitled Understanding Fingering. I think this is an important exercise. It's important to those of us on the set here because it's the last one in the course, but it's also important to you because there are several things that I can emphasize about viscous fingering from the results of this module. We're also going to gain more experience in SI units, and in particular this is a very interesting problem in SI units. We're going to illustrate typical magnitudes for critical velocities and critical wavelengths, and finally we're going to investigate implications of those magnitudes. The solution to this exercise in a summary page 21. Basically, the exercise is pretty much using the formulas that were in the workbook and on the tape and plugging in the values, doing the units conversion, and then finally getting the final result. The first step asks you to take the formula for critical interstitial velocity, and calculate that with the values known. Here's the formula right there, understanding fingering, and the values that we give you are substituted in the formula across. If there's a difficulty in this, it involves what to do about this relative mobility term. The numerical value on it is 10, but the units are reciprocal millipascal seconds, which means that in the denominator there should appear 10 to the minus 3 Pascal seconds in the denominator because it is reciprocal. And what I've done on the key here is just put the units in, made a small amount of conversion over here from cubic centimeters to cubic meters, and the critical velocity then will come out numerically, value of 3.3 times 10 to the minus fifth grams pascals per meter cubed. But then I can remember the definitions for pascals, Newton per meter squared, and the definition for a Newton, which is kilogram meter per second squared, and finally the final conversion between kilograms and grams to work out the units on this superficial velocity. And I get a number of 3.3 times 10 to the minus 8th meters per second, which is 0.033 micrometers per second. And you will recall from our earlier discussion that 3.5 micrometers per second is of the order of 1 foot per day. This translates, therefore, into a superficial velocity that is substantially less than 1 foot per day. Substantially less than 1 foot per day. The critical velocity, therefore, is usually, and in this illustration it is true also, much less than a practical economic rate. So usually economics will dictate that you cannot stay below the critical velocity. Yes, John?
That critical velocity meaning that you would have to have a flood rate less than that?
Yes, that's right.
So that's
right.
Pretty slow.
That's very slow, and so you must take the choice of whether you want a very slow efficient displacement or very fast or fairly fast inefficient displacement, and generally you take the money up front. This does not mean that it is not possible in all circumstances, because if gravity forces are strong, the dip angle is high, permeability is high, density difference is high, it's possible to get a fairly substantial critical rate, and you might be able to stay below it. But in a lot of cases, certainly this is true in water flood, it is uneconomic to stay below the critical rate. That was the answer to the second step. The third step deals with insights gained from the calculation of critical wavelength. I give you a velocity in terms of meters per day, which we're going to convert over into meters per second to be consistent with the velocity of critical velocity in the first part of the exercise. And here is the formula for critical wavelength. Notice that in order for this to make sense, the velocity must be greater than the critical velocity. And we said this was a condition that failed the stability criteria that we established at the very first. So this number is required to be positive. But what else is in the formula is our old friend, the mobility ratio, and something that is different. This is a dispersion coefficient, or if you like, you can think of it as a diffusion-like phenomena. Basically, it is mixing due to random variations in the flow path or random fluctuations in the mean free path of the molecules. And this has a tendency to make the critical wavelength larger. But let's put the numerical values in here, and if I do, I get a number that is about 2 centimeters. This number is almost always 2 centimeters, regardless of the circumstances of the displacement. For you see, the mobility ratio, which can vary a lot, appears in such a fashion that its effect is essentially negligible on the formula. This quantity right here is a function of the medium and the properties of the fluid, and it does not vary very much. We've already said that critical velocities are usually much slower than actual rates. So what we're saying here is that the critical wavelength is essentially driven by the velocity of propagation, the reciprocal of the velocity of the superficial velocity. And for a typical rate, 0.06 meters per day, I get a critical wavelength of about 2 centimeters, which turns out to be the case on almost every case you choose to calculate. But it has some interesting things, some interesting implications about the tendency for fingers to form in various circumstances. Because we said a necessary and sufficient condition for fingers to form was, first of all, that the critical rate be exceeded, and second of all, that the lateral extent of the system be large enough so that the critical wavelength can get in there. In other words, the lateral extent must be bigger, preferably a lot bigger than the critical wavelength. What do you say about the likelihood of fingers forming in a slim tube? Myra?
I would say that's fairly small. Your critical wavelength is 2 centimeters, and I think that the slim tube experiments, the maximum was less than 2 centimeters.
Yeah, the biggest one was 2 centimeters. Most of them were of the order of half a centimeter. In fact, the lateral extent on a slim tube is, by design, fixed so that the fingers can't form. That's why it is that way. Here's another reason for saying that slim tube give you arbitrary or artificial displacement results, because it has been designed to suppress an important phenomenon, namely viscous fingering. How about the likelihood of fingers forming in a field displacement?
Very likely.
Very likely. The lateral extent of the field is, tens of meters? Mm-hmm. Much greater than critical wavelengths. So you can almost count on it if the original stability criterion is violated. How about in a core? Yes, Myra?
I would think that would depend on the core.
It depends on the core, and certainly depends on the velocity at which the experiment is being run. Sometimes one can fool yourself, and in fact there is a history of doing this. People used to do miscible flooding experiments in the early literature, where they would report extraordinarily high recoveries in cores, and then they took the process to the field, and instead of getting 90% recoveries, they started getting 15% recoveries, and there was a good deal of dismay. But basically the origin of that dismay was simply, at that time, the idea behind the critical wavelength and its importance had not been explored. One more thing. If we want to do a simulation, and we would like to do one such that fingers form in the simulation, what do we have to do? What's the likelihood of fingers forming? John?
We'd need to have grid blocks that were on the order less than the 2 centimeters.
Yeah, in fact, we've got to have grid blocks that are critical wavelength or smaller. Mm-hmm. Practical?
Hardly.
Think you could do a large field simulation with 2 centimeter grid blocks? I think even with advanced computer technology, that's not possible. Pretty tough. We're kind of up against it here. We just said that slim tubes don't have them. We just said that field cases support the fact that it is an important phenomena. We just said that core flood results are erratic. And finally, we said that simulation won't predict them. So we're kind of between a rock and a hard place. There is some discussion in the workbook about the resolution to that question, but it is, in my opinion, not fully resolved yet, and it is subject of active research interest. Does anybody have any further questions or comments? Yes, John?
Yes. You said that these fingers are caused by little perturbations at the front.
Right.
What might cause these little perturbations?
Oh, it takes hardly anything. A very small perturbation in the, well, I shouldn't say very small. Actually, there's some evidence accumulated now to suggest that it takes some random perturbations, but they don't have to be of great magnitude. Certainly perturbations of the order that you would encounter in a core.
Such as heterogeneities?
Heterogeneity, yes. Heterogeneities would do it. Anything that causes one point on the displacement front to get out in front of another point.
Mm-hmm. Also, that critical wavelength that was calculated, is that in all directions from the front, or is this a two-dimensional phenomenon?
It's a two-dimensional. Actually, it's a three-dimensional analysis, but the critical wavelength is the dimension lateral to the propagation. Okay? And a more proper way to say it is that the critical wavelength must be smaller than the minimum lateral dimension, okay, in order for fingers to propagate. Okay, so much for viscous fingering. I'd like to reiterate that this, I believe it to be an important phenomena. If you remember back to one of our previous figures, I was showing recoveries in core floods that were in the 90% for developed miscible displacement. But all the way back in Module 1, we said a typical recovery in a field displacement for a solvent flood was 10 to 15%. That's about a factor of 8 or 9-fold difference. And very likely the main culprit that causes that discrepancy is this phenomenon of viscous fingering, certainly exacerbated by all the other non-idealities that can occur in a reservoir: heterogeneity, nonlinear flow, and gravity, and those things. Yes, John?
Is this fingering more a problem in this EOR technique than some of the others?
It's certainly more a problem in this technique than it is in thermal, because of the self-correcting effect that we mentioned. I guess the answer to your question is yes, because in micellar flooding we have a means, in polymer flooding we have a means of correcting it by making the mobility ratio lower. Here we don't really have a very effective means of correcting it. There are some ways to do it, and there is no self-correcting mechanism. So probably it is the single biggest detriment to a high recovery efficiency. Right? Okay, let's talk about some typical results. And in these typical results, I will try to point out to you or reinforce some of the things that we have already seen with respect to the phase behavior, and most particularly to the displacement mechanisms. Let's start off with a core flood result. One of my purposes behind doing this is to contrast this to the micellar flooding core flood that we saw in Module 5. Here's the reported results of a core flood in a Berea core. The vertical axis is the fractional flux, or the fractional flow, and the horizontal axis is the throughput in dimensionless time. This is a core flood that was originally started off at tertiary conditions. So initially the core produces only water. This is the curve for water. The green one is the curve for oil, and the yellow one is curve for solvent. But I'd like to draw your attention to the response of the oil. Now, it's a tertiary flood, and the solvent, in this case CO2, did in fact develop miscibility with the oil. But remember in micellar flooding how we said in a core flood the micellar solution banked up the oil and produced a large fraction ahead of the surfactant as clean oil. Such does not happen even in a core flood here. In fact, the solvent is a little bit ahead of the oil, and rather than a displacement, you might fairly characterize this process as sort of a dragging. The oil is literally being drug out of the core rather than being pushed out the core. So there's a long simultaneous production of solvent and oil, and the oil peaks very rapidly and tapers off rather gradually. Why are they breaking through together? Myra?
Viscous fingering.
Have to be viscous fingering. In a Berea core, about the only explanation it can be, since it's a relatively homogeneous circumstance. Yes?
Well, it's easy to imagine that could be a production history from a field test as well. And my question is, how does this production history differ from that you would expect from a high perm stringer, for example?
Hard to tell the difference. In fact, there's a good chance that there is no practical difference between cycling through a high perm streak and a viscous finger. All I can say on that score is that viscous fingering has been observed in laboratory homogeneous scales, so we know it is a phenomena, but certainly whether it is more important or as important as heterogeneity in a field scale displacement, I don't think anybody can really say. What we can say for sure is that what heterogeneity is that is present there, the effect of that is greatly exacerbated by the unfavorable mobility ratio. Okay. Any questions about the core flood? I'd like to talk now about two field case histories. Both of these things are in their own right sort of clever projects. And I've selected these because they are basically worlds apart in solvent flooding application. The first one is the field results for the CO2 flood in the Slaughter Estate unit. Actually, this was a sour CO2 flood. 20-some-odd% of H2S dissolved in the CO2, which, as we've already seen, will enhance the miscibility of CO2. And this is a flood being done in a West Texas carbonate reservoir of the order of 5,000 feet deep, modest viscosity crude, and very tight, 10 millidarcies or thereabouts. It's a very well-conceived and executed test. Amoco is the operator. And on this plot, on the vertical axis, we are showing oil rate in black and gas-oil ratio in yellow. Horizontally, of course, we are showing the time. It was intended to be a test, so what Amoco did was come in the middle of a larger field, put two small, contiguous 5-spot patterns together, and they wanted to test CO2 in a true tertiary mode. So before they did anything, they began a water flood in the project, and you can see the response in the oil rate to the water flood. Water flood did pretty well. Okay? And then after that, they followed it with CO2, but they did not jump the gun on it. They waited until there was a well-established decline to the water flood such that they could extrapolate it, and then they put in the CO2. Sometime after that point, the CO2 response began, and as we saw in Module 1, the incremental oil recovery is the difference between what happened and what would have happened, and that is the shaded area here in the figure. Notice, just as we saw in the core flood, gas-oil ratio is a manifestation of solvent being produced, and just as we saw in the core flood, solvent begins to be produced about the same time that the oil rate starts to go up. So there is an evidence of something that is causing channeling, either heterogeneity or viscous fingering or something in this field test. One other thing that's kind of of interest is if I look up here, I see that there are substantial fluctuations in the gas-oil ratio, and what this has been is basically fluctuations that are associated with the alternating water and gas injection. Amoco is a proponent of the WAG process, and so in all their processes they inject CO2 and water, not simultaneously but alternating, and they have found that they can detect in the gas-oil ratio the frequency of the different slugs, and that accounts for some of the erraticness, not just back here but also back in here when the gas-oil ratio is increasing. Yes, Myra?
How does the corrosion with CO2 affect the economics of the process?
Well, it's not something to be seized at. I guess I don't know the answer to your question in detail, but I can say that it is a problem. It is particularly a problem in the case here, what is the sour CO2 stream. As you know, CO2 dissolves in oil, dissolves in water, and forms a mild acid, carbonic acid, which can cause corrosion problems. And similarly, H2S dissolves in water to form a very strong acid, sulfuric acid, which can cause corrosion problems in spades. And so there is no doubt that corrosion, particularly with production of the solvent and water simultaneously, is a problem. But I believe that it has been factored into the economics, and the process appears to be economic even so. Amoco is continuing testing of this process in the same field as we speak. Very interesting. One last thing on this one. The incremental oil recovery represented at the date of this transparency about 15% of the original oil in place. In 1985, that number has climbed up to about 20, in the low 20s, 24% of the original oil in place. And if I take the oil produced from the CO2 flood and the oil produced in the water flood and add to it the oil produced in the subsequent primary production, I get a total aggregate recovery in this project of in excess of 70%, which is a phenomenal recovery efficiency in any reservoir, particularly in a carbonate reservoir. Questions, John?
Yeah. Is there any evidence that the WAG that was used on this process helped or hurt them?
Yeah, I think there is a little bit in the sense that it helped them because because of the fluctuations out there. You see, every time you put in the water, and after you follow the water cycle with solvent, very likely you're diverting some of that solvent into low permeability stringers, and so that probably accounts for why the rate is staying up, at least partially accounts for it. The other case I'd like to discuss with you is the Weeks Island case, and this is an interesting case which I can only deal with briefly. This is the top of the Weeks Island structure. It is a gravity stable displacement, and Shell is the operator. What makes this case interesting is the fact that it is gravity stable and how they went about enforcing the gravity stabilization. Here is a cross-section of Weeks Island, and it is miles apart from the carbonate West Texas reservoir. It is an unconsolidated 1 Darcy sand. This particular case is a very high dip angle, very few wells. The dip angle is about 45 degrees. And what Shell intends to do on this one, or is doing right now, is first of all to begin a water flood in downstructure wells, produce in upstructure wells, because gravity effects are important. There will be a water oil front that moves up the structure horizontally, flooding out the zone. And once that front moves high enough in the structure so they can detect it in the wells, then they will convert this well back over here into a water producer, and they will begin injecting CO2 at the top, and it will be a gravity-stabilized tertiary flood now coming back down the structure. And they have been monitoring the progress of the flood by detecting the migration of the CO2 displacement front and also the front of the oil bank in logging observers. There's more details of this flood discussed in the workbook, and I think I commend it to your attention because I believe it is a very interesting case and certainly radically different than the Slaughter Estate Unit. Let's summarize the module. Module 8, entitled Acquiring Solvent Flooding Basics. What I think are the important features in here are the fundamentals. It's important to understand the distinctions between the different solvent flooding classifications. It's also important to be able to use minimum miscibility pressure correlations and understand the trends in them, and also to be able to make quantitative calculations. And finally, I think it's important to be able to understand the displacement mechanisms, most particularly viscous fingering and the things that cause that to be important. Does anybody have any questions about module number 8 before we go on? Great. I think it's time now to wrap up the course. One of the ways we can wrap up a course is by doing some more comparisons like we did in Module 1. Another thing that we can do is sort of compare screening criteria that indicates a favorable application of these. Unfortunately, it's not as clean and it does not give as good a comparison as I would like because each process has its own set of screening criteria. So what I shall do is basically refer to some common reservoir parameters, basically oil viscosity, permeability, and depth, and compare the applicability under current technology of the major processes that we have covered. The information I'm going to share with you comes from paper by Tabor and Martin, and the diagrams, in fact, come straight out of that paper. There will be 3 figures of the fashion shown here. On the extreme left will be listed the UOR method, and this classification is more refined than what we have been dealing with in the course. The first 3 methods here are what I was calling solvent flooding. Next is surfactant polymer, which I called micellar polymer. Then there's polymer, then there's alkaline, in situ combustion, and finally steam drive. If you want to follow along in the text, the best place to do this is on summary page number 25, which are the last few pages in the entire workbook. Going across the top of it is an axis, a logarithmic scale that shows the values of the particular parameter of interest. And it may be a little difficult to read the lettering, but all the way through here, an area that is heavily shaded is an area that is not feasible for that particular process. If it is lightly shaded, it is an area that is difficult or more difficult than the heavily shaded area. And finally, if it is not shaded at all, it is a range of the variable that is favorable for the process. So with that sort of shading code in mind, we can look at these things now without actually having to read what is on the figures. And starting from hydrocarbon miscible down to steam drive, we see there is a progression of increasing oil viscosity for more favorable reservoirs. The hydrocarbon or the solvent flooding processes tend to be those processes that work better in light oil reservoirs. Little higher viscosity reservoirs, higher viscosity crude oils is where surfactant and polymer comes in. And finally, at the very extreme case, is fire flood and steam drive. As I mentioned earlier, steam drive can probably be done in light oil reservoirs, but at that point is probably an unfavorable competitor with respect to water flooding. Also of interest over here, even in the very high viscosity cases, 1,000 to 10,000 centipoise, there is a substantial area out here where not even the thermal methods will touch, which is to say that there is a lot of crude oil, heavy crude oil, in the United States and elsewhere, which even our very best techniques cannot get at today. This is a subject, of course, for some exotic techniques or some new research ideas, and all of those techniques are being worked on in one form or another in industrial and academic laboratories. It's interesting also to look at depth as a panorama. And here is the same sequence from hydrocarbon miscible down to steam drive. And this is kind of an inverse sequence to the centipoise one, because the solvent flooding methods tend to be those that work best at the greatest depths. You know why?
Excuse me. ternary diagram has a tendency to shrink at higher pressures.
Right, greater depths associated with higher pressures, and in fact there's more of a tendency to develop miscibility at those higher pressures. Notice the CO2 flooding, the depth limitation comes up a bit because, as we have seen, CO2 really develops miscibility at a much lower pressure than either of the other two processes. But as I move on up here, there is a depth limitation for the solvent flooding processes at the upper end of the depth because of the pressure limitation. But when I get to the chemical flooding processes, the limitation on depth is on the lower end. I can't go too deep. Can't go too deep. And the reason for that is, as we've discussed, is basically the thermal instability of the polymers and other chemicals used in this process, and to some extent the fact that deeper reservoirs tend to be more saline. If I go down in here to fire flood and steam drive, I notice that there is a great discrepancy in the depth limitations, or the permissible depth, between in situ combustion and steam drive. Normally steam drive is shut off at the order of 3,000 feet, and the most common application is far shallower than that. Below about 3,000 feet with current technology we cannot go. Fire flooding can go much higher. There is in fact not a technical limit on fire flooding at the great depths. The limit is economic, the compression costs associated with it, compressing air, and keeping the fuel rate constant. So a heavy oil reservoir that is at great depths is almost certainly a fire flooding candidate. The last thing that I'd like to compare like this is the permeability guides. All of these things are not necessarily independent of each other, of course, but we're going to treat them as such. For the solvent flooding methods, permeability doesn't seem to matter. Doesn't seem to matter at all. What matters more is if the permeability is uniform. They're not high permeability stringers or excessive heterogeneity. For surfactant chemical flooding methods, there is a limit, a lower limit, on the permissible permeability, and that we discussed in the chemical flooding section, where we talked about how there was a lower limit on the size of the pores that the polymers could be propagated through. For the thermal flooding method, there is a lower limit, and this lower limit is greater than the chemical flooding methods. It's of the order of 100 millidarcies and maybe even higher. And what this is a manifestation here is of higher permeabilities, or I should say low permeabilities, generally mean low porosities, and low porosities mean a lot more rock to heat up and a much bigger source of heat loss. And so the efficiency of the displacement is much poorer into those circumstances. Well, it's easy to compare the three graphs and find areas where there's no technique that can touch anything. It's also easy to compare the graphs to find areas where all techniques will work. And in those circumstances, one must compare them all on an economic basis. And again, there is no general rule for that sort of comparison. I think that's a very useful comparison, and that's basically the point where I'd like to stop the course at now. Let me conclude with one more visual, and that basically is the course outline. We've gone through an overview section, we've gone through introductory material on displacement fundamentals and phase behavior, and then we have talked about the individual processes associated with chemical flooding, micellar polymer, other chemical, thermal methods, and solvent flooding. Where we're going to go from here, I think only the future will tell. Currently, the research emphasis is in methods to develop or improve mobility control in steam floods and CO2 floods, and also for developing more salinity and thermally resistant polymers. I think that some of these things are almost certainly going to work, and I believe that they're going to work to the extent that we are going to realize that 28 billion barrels of potential target oil, potential EOR reserve oil that we talked about this morning on the NPC slide. Thank you very much.